Now you can see that should be.
So, I've pulled some images off of the camera back there for my different classes, and I noticed during the middle of class how many of you who have your laptops open are doing things completely unrelated to class. Now, I don't necessarily care, but your quiz grades are certainly reflective of this. For those of you who have like a 30% quiz average and you're sitting there surfing Facebook or playing games or something like that during class, this crap isn't necessarily easy, but why pay your tuition if you're just not going to pay attention in class? Just don't show up. Get the 0 in the quiz. Or show up, you'll probably get a 30. If you show up, you get your 30% charity grade for your quiz, just so you're one step above the person who didn't show up to class. But you might want to pay some attention in class because this stuff is actually useful for like your careers when you go and do something. Otherwise, you'll get out of here, you'll have a computer science degree, or maybe you won't, but you get a computer science degree and it'll just be a piece of paper. You'll walk into some place and you just bomb the interview because you're an idiot. So it's something to consider. It was actually kind of shocking how many people were doing other things. You have this perception that, when somebody has their laptop open, they're taking notes, which is perfectly acceptable. But and actually sometimes it's not really shocking. Like when Haxton's sitting there and he's laughing because they're watching YouTube videos or something like that. It's like, at least fake it. See, with the older laptops, you used to be able to tell because they used to have the Ethernet port on the back of them with the blinking lights. So when they were on the Wi-Fi, you could actually see it flashing. Like, okay, that guy's streaming something.
When they put two, that's when you know they're trying to hide it.
Yeah. Maybe I should make a policy. You have to turn your Wi-Fi off during class. But that would indicate that I care. It's like your props that make you. How many of you have props that make you that don't allow you to use laptops or make you put your phones away or something like that? What do you think about that?
I prefer to take notes on the laptop, so it just bugs me on that.
Yeah, I personally think those policies are stupid. I mean, if we were in third grade, I could see it. You guys are adults. Pay the consequences for your errors. I get paid either way.
Like they're worried about getting distracted so much. It's like if you choose to not pay attention.
That's it. And the perk is actually that if you fail the class and you have to take it again, then I don't have to worry about not having enough people in the next version of the class. We have repeat business. Take 325. Take it often. All right, so this was from the stuff we did last class, breaking these things into nibbles. Remember that? So we're going to take this dude. There's our nibble. There's our nibble. We'll go ahead and pad this guy. Right? 0, 0, 1, 1 is what value? 3. 0, 1, 1, 1 is what value? 7. 1, 0, 1, 1 is what value? It's an 11, which is a B. So number 1 was 37B. See how easy that was? Second one. B is 1, 0, 1, 1. A is 1. Here, I'll do it in bit. Nibbles. What's A? What's a 10? It's 8. B, 1, 0, 1, 1. 1, 0, 0, 0, 1. And 3, 0, 0, 1, 1. So that was the answer to the quiz. Did you need 4 minutes for that one? In hindsight? Did you need a calculator for that one?
Nope.
Did you do it this way?
Yes and no.
Okay. So we see the benefit of that, the nibble, the binary to hex and hex to binary using nibbles. Makes it real easy, right? Okay. So historically, how would we have done this? Just out of curiosity, you'll get credit for it if you wanted to take it a long way, but it might have been difficult to get it done in 4 minutes. How many of you tried to convert from binary to decimal, then decimal to hex? Okay, you would have gotten the same answer, but it would have taken a lot longer, right? We would have gone through here, and this is the ones place, the twos place, the fours, the eights, the 16s, the 32s, the 64s, the 128s, the 256. The 512, the 1024, the 2048. Do the math, get your decimal number, right? Then divide by 16, record the remainder. Divide by 16, record the remainder. Divide by 16, record the remainder. Read from bottom up. Get your answer. Down here, what would you have done? How do you convert? Old school, how would you have converted a hexadecimal number into its decimal equivalent? I'm sorry, into its binary equivalent. We would have started by converting it into its decimal equivalent. This is the ones place. This is the 16s place. This is the 256th place. This is the 2048. This is the 16535. Oh, am I doing that wrong? 16s, 30, no, 16s, 16 times 16 is 256, yep. Times 16 is 4096, oh, that's where I made the mistake. Times 16 is 65,536. Mr. Quiz.
I know. Unfortunately, I know.
But then again, so did most of these people.
I made it from downtown in 13 minutes, and I spent 5 minutes looking for a parking spot.
Well, why were you cutting it so close?
I got caught up in a meeting and lost track of time. I didn't even eat today. That's how bad it was. I had 7:30 breakfast.
I had blood work this morning, so I had to fast for it. I had to wait till 8 a.m. and they took 13 vials of blood for all the, because I'm having a whole bunch of different tests like my thyroid and stuff.
You were feeling wonderful.
I don't know if you guys have noticed, but I've put on about 60 pounds in the last 3 months. And I've been exercising every day, so something's wacky with something. So they're doing all these tests to figure out like what's going on with my thyroid and stuff. This lady's just taking vial. She had to switch to another vein. then they let me walk. Then they let me walk out of that place on my own to drive a car.
Would you like stumble out the automatic door?
I actually felt fine,
Did they give you
surprisingly.
Did they give you any sugar?
They gave me like an apple juice thing, yeah. And then I went and just rode through McDonald's real quick and grabbed a couple of sausage biscuit things.
And you wonder why you're gaining 60 pounds.
Well, I typically don't eat sausage biscuit things from McDonald's. I usually just eat a gallon of ice cream for breakfast.
Or a buttered rounded burger, it's obvious.
And that makes no sense at all.
Yeah, well, the difference is I was doing all that stuff before. And then what I included in the summer that I wasn't doing before is a bunch of exercise on the golf course and gained weight. So I've never eaten healthy. It's not like I went from a healthy to unhealthy. Well, actually I was eating less over the summer. My appetite was a lot less. So who knows?
It's like the one guy. It's like, oh, getting back in shape. No, I never was.
I was never in shape. Rounds of shape. All right, so this makes sense. That conversion. All right, if we look at our code from last time, did we even implement this? The conversion thing?
We've got it displaying.
Did I do it all inside test?
Yeah.
Oh, display nibbles. Okay, so we got it displaying. So we've just gone through and displayed the nibbles, right? No, we converted. What's up?
You have your map there, so.
Yeah, we got the conversion. So here, let's walk through this. So we take a binary number, a string representation of a binary number. So for example, we could take this binary number. I'll take the spaces out of it. we got this binary number. $37B. Okay, so we have our binary number for today. We pass it into display nibbles, which we were just doing that before, and then we added a little functionality to it. So what does this guy do? The first thing it does is it figures out how many extra zeros do we need. Why do we need extra zeros? Why might we need extra zeros when we're converting from a binary number to a hexadecimal number?
So nibbles are half nibbles, not half nibbles.
Okay, so we're modding by 4 because we need to make sure that we pad the number with enough zeros in the front so that we have equal nibbles, a bunch of 4-bit blocks, so we're not left with a 1 or a 2 or a 3-bit block on the far left. Make sense? And that's what we had to do up here. The number I originally gave you was that. That was what I originally gave you in the quiz. You had to go through and notice, here's a nibble, here's a nibble. This isn't quite a full nibble. Tack on 2 zeros. Go ahead.
Can you go back to your code?
No. That part makes sense? We'll go back shortly.
Well, something's okay.
You can't figure out yourself, you have to copy my code?
No, I'm not.
Did you fail this quiz?
No, I got it.
Answer the question. You got both of them?
Yeah.
Did you do it the right way? All right, I'm proud of you. I'll go back to the code.
Add a 1 to your string
Where?
at the beginning. I
Here?
guess I don't think it really matters.
Well, add a 1 right now.
Yeah. And then push play. Why does that happen?
Let's see. 1, 2, 3, 4, 5, 6. All right, so that is 13 bits, right? 13 bits. So 13 mod 4. 4 goes into 13 how many times? 3 with remainder. 3 times 4 is 12. That's a remainder 1. So we get a num 0 of 1. That's actually not what we want, is it? What do we want? We need 3 extra zeros. So really what we want here is we want 4 minus this. It just happened to work on our other one because it was 2. 2 extra zeros or remainder 2 just happen to be the same value. That make sense? So this is what's left over. Our shortcoming of zeros is 4 minus that. See, I put that bug in there for you to find. Actually, this was from last class. Why didn't you catch this last time?
I did. I just didn't say anything.
Yeah. Took you 48 hours to catch that bug that I inserted on purpose.
Probably goes back and reviews the videos and just like goes through every line of code, sees where you're wrong, and comes to the next class.
No, not sees where I'm wrong. Sees where I purposely inserted bugs for you to for you to find. 2 very different things.
Get rid of the one that you put on the front and then play it.
Get rid of this one?
Yeah. I wonder if it's going to be the same. Why does it have that extra 0 in?
Because you have a 0 bit at the beginning. You're reading it from down up.
Okay.
So 0378 is the same number as 378.
Okay. I was just making
So this is the 1s, the 16s, the 256, the 4096. So that's 0 times 4096, which is nothing. So that's the price we pay for, yeah. Okay, so there's our one from the quiz today, though, right? 37B. So this part of the code right here, just make sure that we have an even number, well, not even number of nibbles, a number of bits evenly divisible by 4 such that everything can be subdivided into whole nibbles. All right, so that's everything that is highlighted there. That's what it does. Then we're going to build up our answer in temp. We have our mapping value that allows us to map from, a digit of 0 goes to 0, a digit of 10 goes to A, a digit of 11 goes to B, so on and so forth. So now we're going to spin through this. We're going to build up an individual nibble. We're adding 4 to I each time. So we're going to grab a nibble inside a temp, and then we're going to print out that nibble, which is in base 2. We're going to get the decimal version of that nibble, and then map it on our map string. So if the decimal version of the nibble was 10, we would get an A. The decimal version was a 3, we'd get a 3. So on and so forth. And then we're going to print that out. Okay, so we can rename this if we want. Maybe we call this guy bin2hex. And maybe we say that this guy is going to return a string. So let's go ahead and give ourselves a string answer. So then rather than printing this out, we're going to say answer is equal to answer concatenated with, except let's just change that plus sign to an equal sign like I said. Answer is equal to answer concatenated with the mapping of the decimal version of our binary. And then in the end, return answer.
Still gotta print it.
Yep. So this is going to call the method. Method's going to calculate the answer, return it as a string. I can catch it in a variable if I want to use it for something else. And then I can print it out. There's our 37B. Make sense?
There's no variable specifically designed to hold hex, is there?
There's not. I think there might be an object in Java outside of strings that can work with hex, because strings can work with hex. You can hold a hex string and then convert to decimal.
There's no like pre-built.
I don't. Not that I'm aware of. Which doesn't necessarily mean.
I'm sure there's someone.
Oh, we could write one, certainly. But like I've said before, I mean, I've been writing Java since the day it came out, and I'm sure I know have used less than 20% of the entire language. There's just aspects of it that I've never run into problems that I had to go and use random class X for something. So it's entirely possible one exists, but I'm not familiar with it. Okay, so. Just out of curiosity, what would you want that class to do?
Just
conversion stuff like this?
Yeah, just like basically, if you were to, Java's not really good at reading your RAM, so that probably wouldn't be very beneficial. But if you were to go in and read the RAM of a program and display, like.
Well, really, Java's incapable of reading the RAM.
Yeah.
Yeah.
It is,
Yeah. The nature of a virtual machine.
Yeah.
You can only read Java's fake RAM. But if we went to a language like C# or C++ or C, where you could actually access real RAM, having a conversion class that allows you to deal with the index, but even then, you'd have to store it as an object. Because that was something. Well, that was something that Abe was telling us. The reason we use hexadecimal as our kind of our counter to index through RAM is because if we were using decimal, the number would get too big. We couldn't even store it in a long, right? So that's why we do, not only are we counting, but in hex, we're also, our buckets, we make them large enough to hold something useful. So maybe when we talk about hard drives in the operating systems class, we're going to talk about block size of each individual container of your hard drive. In memory, we usually talk about them as frames. Frames and pages that fit into frames, and what's the size of a frame. You know, for instance, something we'll talk about in there is the most efficient use of storage space for memory would be to have every frame be 1 bit. It's horrifically inefficient for almost every other situation, but you do maximize your use of RAM. Because the smallest thing you could store in an individual bucket is a bit. It becomes very expensive. Imagine taking your 32 gigabytes of RAM and having to count how many individual bits that is as a number. Now index that. It becomes unwieldy. Okay, and we'll talk about all the pros and cons of that. Okay, so now we're going to write another method, hex to bin. This guy's going to take in a string s as a parameter. Okay, and we want to get the hexadecimal version of that value. I'm sorry, the binary version of this hex value. And we're going to do that, just like from the quiz today, taking each of these digits and getting the binary equivalent of it. Right? How do we do that?
Your map could be an array instead of a
Okay, an array of what?
strings.
And what would each string be?
The character equivalent to a hex value. So 0001 for
Okay, the binary equivalent
Yeah.
of the hex value.
Yeah.
Okay, so maybe we have a array, string array, we can call it map, and this guy is going to be equal to string 0000, that's a 0, 0001, 0010, 0011, 0100, 0101, 0110, 0111. 1000, 1001. That's 9, right? Here, let me actually kick this down a line just for organizational purposes. So now we're at 9. 10 is 1010. 11 is 1011. 12 is 1 1. That's 8, 9, 10, 11, 12, 1 1 0 0. 13 is 1 1 0 1. 14 is 1 1 1 0. 15 is 1 1 1 1. I got an extra comma up here in a couple of places. Notice how nibbles happen to add up to, the biggest number we can represent in a nibble is, the biggest unsigned number we can represent in a nibble is 15. Smallest unsigned number we can represent as a nibble is 0, which just happen to be the digits of binary, or digits of hex rather. And this is a shortcut way of defining arrays. Rather than saying, you know, string array map equals new string array 16. Bucket 0 equals this, bucket 1 equals this, bucket 2 equals this, so on and so forth. All right, so now we have lookup nibbles. But now we need to also have, here, actually let's call this nibbles. And then let's create a string called map. And we want the string map to have all of our hexadecimal characters in it. Then we're going to have a string answer that's going to actually hold our answer that we're going to build. Now, we want to go through S one character at a time, where S might look something like this. BAB13. And we're going to take this B. We want to find out which hexadecimal digit that is in decimal. So we need to convert that to an 11, first of all. How do we get an 11 from our string map? If I gave you string map and I told you that I want you to be able to take a B and get an 11 out of it, how would you do that? Go ahead. Index of. So if I say map.index of B, it's going to give me the position of the first occurrence of B in that string, which happens to be at bucket 11. And then if I go, give me whatever's at bucket 11 in nibbles, this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Is that the binary version of B? So we're going to say for int I is equal to 0, I is less than s dot length, I plus plus. So spin through every character in S. And each time through, we're going to say answer is equal to answer concatenated with, well, let's do map dot index of s dot char add I first. That's going to give us our position number. For instance, if it was a B, it would give us an 11. And what am I going to do with that 11? I'm going to go nibbles at bucket. In this case, for that example, would be 11. So this would boil down to an 11. Nibbles at bucket 11 would say, give me the string that lives at position 11 in nibbles, and I'm going to concatenate that on to answer. And at the very end, return answer. And that's hex to bin. We can test that with our example here, BAB13. String hex is equal to BAB13. We'll just print it out directly. System.out.println. That's the name of my class. Test.hex to bin. We'll pass it our string called hex. Print out the answer. We're hoping it gives us this guy. We'll copy this real quick. Oh, perfect. Same value? All right. Now, you see how concise these algorithms actually were? There's not tons of code in there to do that. Probably the hardest part of this one was padding. Did we actually need to pad here? Would this algorithm work had we not padded in bin to hex? The way we wrote it, we would have had problems, since we assumed steps of 4. Could we have done that differently?
If you went back to front, probably that
So if we would have went from the end, knowing that we're just going to take chunks of 4 or less. So if we have something, a string that's less than 4, let's just take what's there. This guy would have worked. So this does not need a nibble to convert to binary. So we probably could have gotten away with it then. All right, so that makes sense? The conversion from hex to binary, binary to hex using nibbles. Very convenient for us and very quick. Even a human being can do it very quickly. But the algorithm for writing this is also quick. Before we knew how to do that, if we were to write a function to do that, we probably would have written it the same way we would have done it as a person. Hex to decimal, decimal to binary. Or binary to decimal, decimal to hex. We would have done 2-level conversion. We already had those methods written, so we would just call those methods separately. But there would have been a lot more steps to accomplishing it. Okay, so now that is convenient conversion between hex and binary and hex. Well, we also have a third base that we use often. And that's decimal. So binary, hex, well represented in computers. But decimal, very well represented for people. And often it represents the inputs from our computer programs, right? You might enter in a decimal number, and now we need to convert it to something in such a way that it's convenient for computers. Now, right now, if I want to take a decimal number and I want to convert it to hexadecimal, what do? I got to go through my algorithm, right? What if I want to convert it to binary? I got to go through my algorithm. So it's somewhat involved. Okay, now, the last time we were kind of talking about what it would take to build a hardware version of this converter, right? And when we get to AND and OR gates and things like that, we'll actually be able to fill this out, but we can kind of see where it's going, where this is almost the hardware example of what we did here, what we wrote. Because notice, even down in this bin to hex, this one line here, this is kind of the epitome of a high-level language. This one line here is actually fairly complex. We're calling upon this function, and who knows how long that function is. Longer than one line. That converts between a binary number, and this gives us the decimal version of it. So that converts binary to decimal right there. And then we're calling this char@, method, which is going to be more than one line, which is going to give us one of the characters in this string map. So this one line is actually has 2 different function calls, 2 different method calls within it. So even though we look at it and visually it has a pretty small footprint, reality is it's quite complex. So the same thing is true here. We can probably, with a whole bunch of wires and ands and ors and things like that, come up with something that will light up the right light bulb here. But it's going to look complex. But at the end of the day, this is the hardware version of a computer method, programming method that we just wrote. Does that make sense? We might accomplish it a little bit differently. Because in hardware, we don't necessarily have these high-level programming language tools that we have with Java. With hardware, we're kind of dealing like machine language, or at the very least, assembly language. We're not dealing with just zeros and ones, but we are dealing with zeros and ones. On and off. We're having to deal with it at that level. Okay, so it becomes kind of an interesting thing to program in hardware, if you will. And this is why so many of these devices these days are kind of, if you followed them, there's one called Arduino, which we've historically used in this class, and I actually have a couple, and we might bring them in maybe after midterm somewhere. Then we have some of the new devices, Raspberry Pis are one of them. These are programmable circuit boards. So it's kind of a computer on a chip. Sometimes these are called embedded systems. And what it allows you to do is you have some hardware, and this hardware has a bunch of functionality. So think of it kind of like a simplified processor. So when we talk about processors, we say they have a whole bunch of magic tricks that they know how to do, right? Well, these simplified embedded systems have less magic tricks. There's usually some sort of programming API associated with them. And maybe there's 50 things they can do, and you can solve all your problems in terms of those 50 things. But instead of having to hook up wires and all this stuff, you can write some high-ish level programming code that works with the individual features of that embedded computer, an embedded processor. Kind of makes sense? So it almost creates a hybrid situation between, oh, I'm a hardware builder, and oh, I'm a programmer. Because sometimes programmers want to take something beyond, I have a cool Java program running in Eclipse, to now I have a cool Java program that's making this robot that's running around the floor do something. You know, that's kind of a cool hobby thing, right? That we can make a piece of hardware actually do something real. But it's inconvenient for us to have all these wires and stuff sticking out. It looks cool, looks like you're, this mad scientist, right? If you had this robot, you build a robot in here and you just have wires coming everywhere, and as the thing's moving, it's kind of sparking and stuff, and you kind of know what I mean, right? It's like Anakin built C3PO. I'd like to see like a 12-year-old do that. I'd like to see anybody do that. It's like, oh yeah, just working on this droid. I build him out of the dust. All right, so,
Like you moved that RC car.
huh?
You moved that RC car.
Yeah, and I didn't even build that. I couldn't work with a pre-built thing. That's how bad it was, right? So, in any case, these new programmable pieces of hardware have become kind of fun for hobbyists because it allows somebody who doesn't necessarily A, have the experience, or B, have the patience to deal with every little tiny bit of hardware soldering wires together and stuff. It allows that person to use a whole bunch of ready-made things, whether it's a Wi-Fi controller or LCD screen, all these things that you can plug into this piece of hardware, and then you can write a programming language in the middle which is convenient and easy to change to actually make it do something. So as an example, if we wanted to create a piece of hardware that just displayed, hooray to an LCD screen over and over again and have it flash. Okay, if we did that in hardware, we'd have all these wires that pin out to that LCD screen, and then we have some sort of timer set up where it's a 1 for a period of time, then it's a 0, then it's a 1 for a period of time, then it's a 0, and it would be that. Now let's say we decided we didn't want to say hooray anymore. Now we want to say woot. Well, you got to change up some wires, right? With a programmable controller, we can just go in and change the variable name from hooray to woot, and it'll just work. Because we had software that sits in the middle. That make sense? And this is something that's been evolving for a while, and we've had this at the professional level for a while. How many of you have ever heard of something called firmware? Okay, what's firmware? In what way have you heard of firmware?
It's the go-between the software and hardware.
Okay, and so places where you've maybe heard of firmware is like if you had a router at home and you had to update the firmware in it. Or actually when you get an update to your cell phones, often you're updating the firmware to that cell phone. If you've ever rooted an Android device or jailbroken an iPhone device, typically you are rewriting the firmware of that device to make it act differently than it was intended. Okay, so firmware is very much the middleman between pure software and pure hardware. It's a hardware-based software.
That's where its name comes. Soft and hard in between is firm.
Yeah, exactly. For once, you got something right. Okay. So we've had this around for a while. Was that phrasing? It was?
That was a pretty big case of phrasing.
Was it? Yeah, there was some phrasing the other night. I was playing a video game and somebody was speaking through the speakers and said something, and my wife just starts busting up laughing. I don't remember what it was. But if she gets it, it's usually funny. What was I talking about? Oh, in any case, so something that's been around for a while, like kind of the professional, under the hood level, has now kind of come into the mainstream for hobbyists, where we can now take programmable controllers and write software to make the hardware do something, which makes it much more available to normal people. Because even if you know what you're doing, how many of you have actually done stuff with like soldering wires together and and with building any little hardware stuff. Okay, so yeah, okay. So even that is like tedious, right? I mean, even just soldering 1 or 2 wires, or if you ever, a good example. How many of you ever have modded a video game system? A good example would be the Nintendo Wii, the original Wii. If you modded the Wii, what you would do is you would buy this chip online, and the chip was kind of, instead of paint by number, it was solder by number. So what you would do is you would take this chip and you would overlay it. You'd open up your Wii and you'd overlay it over the circuit board, and it had the holes in the right places on this chip, and basically put solder here, okay? And the chip would have the crossover wires to do all the stuff it needed to do. So all you were doing is you were connecting that circuit. Little liquid metal here that dries, a little liquid metal here that dries, and all of a sudden it's doing the jump. And I think basically the way it worked is on the Wii there was a, it checked to make sure you had a legitimate Wii disc, and what it did is it bypassed that. It just created a jump wire. So rather than it hitting a yes/no gate here, it just went here right to here. So it's always a yes. So, and the thing is that if you were non-technical, that was like kind of hardware modification by number, right? But now when we talk about it from a technical perspective, it makes sense. We bypass the question. And the same thing can be done in all sorts of different, systems. You watch these TV shows and stuff like that when they're, bypassing the timer on a bomb or something. Usually they're connecting one wire to another. I'm not sure that cutting the wire thing would work very often, but looks good in the movies, especially when they say cut the red wire. They should have some interesting statistics. Like, what's the success rate of diffusing a bomb when you cut the red wire?
How many times have bad guys switch the red wire to the red wire?
Yeah, why wouldn't you just do that? Now what do? We don't even worry about that. We just send robots in. The new bomb diffusers, if you've seen these, is you send a robot in, and the robot has like this giant like garbage can, just made of like super thick walled, iron or steel or something like that. It just lifts the bomb up, puts it in there, and shuts the lid and just waits. Why diffuse it when we could just take it in the gut? It's actually interesting, right? I mean, technology has really taken over some of these things, even warfare now. I mean, how long until we're going to have our modern day battlefield players, playing our wars?
Half of our stuff is controlled with an Xbox controller.
Yeah, I mean, it's probably not horribly far from the truth.
No, it's an actual like Microsoft Xbox.
Yeah.
Controller.
I mean, that's what the world's become. So now we're fighting these land wars, and there's not even people involved. Why don't we just flip coins?
Those robots to do the bomb defusals.
Yeah.
It's an actual.
Is it?
Xbox controller.
Yeah. See, I just find that stuff amazing. It's just like the human way out. Rather than figuring out how to defuse it, let's just explode it in a safe way. Although, how many of you saw the movie Angels and Demons? It's actually the prequel to Da Vinci Code, but so at the end of the movie, the guy took the crazy nuclear or beyond nuclear bomb thing up in a helicopter. Did you ever wonder why there wasn't pieces of helicopter falling out of the sky?
Because it's a movie.
Yeah, but that bothered me.
That's what bothered you the entire movie?
Yes. I mean, you're gonna take a helicopter up. Let's say you take it up 10,000 feet, and then you explode a nuclear bomb. It's not going to disintegrate every piece of that helicopter. You're going to have chunks of blade.
You probably wouldn't see any piece because the explosive force outward would just.
So it rained somewhere else, is what you're saying. You're arguing that it did rain down, just not there.
It's like 20 miles away, some asshole's house just got destroyed.
All right, I'll accept that as a possible. Still bothered me, especially since this dude just parachutes down like it was no big deal, right? Wouldn't he have been caught up in that? And like his body kind of.
I think there are a few more glaring problems with that movie than the
Really?
helicopter.
Like what?
Like the entire fact that you have, I forget who the main actor is, but he's some professor that goes around and some guy whips himself, and
Well, that's Da Vinci Code.
that's
Different movie.
Same series.
Yeah, same series. It's true. That's a different movie. The Opus Dei guy.
Is the Angels of Demons the one that are in Vatican City?
Yeah.
I'm sure that there are more problems.
Well, first problem is you got the bad dude being Obi-Wan Kenobi. How do you cast Obi-Wan Kenobi as a bad guy? Makes no sense. All right.
He wasn't the bad guy to start with, though.
Huh?
He wasn't the bad guy to start with. Well, we didn't know he was.
We didn't know he wasn't. Yeah. So if you haven't seen the movie, by the way, he's the bad guy.
That's what happens when the Jedi stop paying.
That's it. All right. So binary math. How do we do math with binary numbers? Convert to decimal. Do your math. Convert back to binary. So let's say I'm adding 1 1 plus 1 0. Let me ask you this. How do we do math with decimal? Here, I'll throw a... So how do we do 50 plus 28? We usually...
What should I do with a calculator and it spits out the answer?
We have our 5. We have our 0. You don't know me? There we go. Perfect.
It's awful.
Pixel perfect.
Nope, it's awful.
Pixel perfect.
I can see.
All right. So we're going to add these guys together. Also, what? We usually have the... See, just like 3rd grade. We're perfect. Okay? So we got these guys. What do? We take the 8 plus the 0, giving us a what? 8. And then we take the 5 plus the 2, giving us a what? 7. We got our 78. Now, what if this was 59 plus 28? 9 plus 8 is what? 17. So what do we record down here? 7. And then we carry the 1 for the tens place, right? This is the ones place, this is the tens place. So now we have 5 plus 2 is 7 plus 1 is 8. Was this your card? That was my card trick. That make sense? All right, so how will we add binary numbers together? So we got 1, 1, and we have 1, 0. One plus 0 is what? 1 plus 1 is what?
2.
So what do?
Carry the 1.
It's 0. Carry the 1. Then 1 plus nothing. We just drop the 1 straight down. So it's 1, 0, 1. So this is what number? This is the number 3. Plus the number 2 is 5. This is 4 plus 1 is 5. Make sense? Exact same way. We do addition the exact same way. What about subtraction? So 1, 1 minus 1, 0. Stay over there. Behave. All right. So 1, 1 minus 1, 0. Well, what should we get here? So this is the number 3. This is the number 2. We hope to get a 1. Correct? 1 minus 0 is what? 1. 1 minus 1 is what? Is that right? So number 1 seemed to work for this one. What if we have 1 0 minus 1 1 0? Well, 0 minus 0 is what? 0. 1 minus 1 is what? We could really throw an extra 0 up here, right? Just to have them have the same digits for visual sake. Doesn't change the value of this binary number. 0 minus 1. It's a negative 1. What do we do with that? If we have 0, 1, 0, that's the number 2. Next one down, we have the number 6. 2 minus 6 is negative 4. Right? So now we have 0 minus 1, which is a negative 1. Where does the negative get recorded? If we think about negative numbers with binary, how do we represent negative numbers with binary? Think back to when you first learned Java and we talked about bytes and shorts and ints and longs and all those guys. So our byte primitive type. Bytes are signed 8-bit integers. What's the range of values they can hold? Plus or minus 2 to what power? Well, byte means what? 8 bits? So it's plus or minus 2 to the what? Plus or minus 2 to the 7th. Why not 2 to the 8th?
You subtract 1 for the plus or minus.
We're using 1 bit for whether it's positive or negative. That make sense? So to represent this as a negative number, we really need to have a sign bit that is maybe 0 by default and 1 to represent a negative number. But this is not part of the value of this binary number. It's only positive or negative, on, off. Make sense? All right, so that's math with binary numbers. Was math with binary numbers really any different than math with decimal numbers? So we took the value 2 here, right? Let me just kind of steal most of this. You need to stay out of my way. I don't have the dexterity to deal with you. All right, so this is actually just a really stupid way of showing decimal numbers, but let's keep it equivalent. So we have 2 minus 6 in decimal. Well, what do we record? 2 minus 6 is what? Oh! That's a 4. And we remember out here that there's a negative number. So we're really using a negative bit there too. But human beings, when we count, we don't think about how many bits we're using to store the value. Or how many digits we use to store the value. We use as many as necessary. Right? Okay? So we're still using the same type of thing. And rather, since we're not binary, since human beings are flexible, we can just say, oh, we'll store a negative or a positive number. No big deal. Well, that's not legit in binary. Binary, we have zeros and ones. Work with it. That's what we have to deal with. Okay? So, makes sense? There really is no difference between adding and subtracting binary or decimal. Now, eventually we'll start talking about something called the 2's complement, which are some other ways of dealing with addition. You do subtraction through addition by using the 2's complement of the bottom number. Not really important for what we're doing right now, but when you think about it from a programmatic perspective, if you're making hardware, you can just do everything through an adder. So we have a piece of hardware equipment, and we'll talk about this when we start dealing with the actual, we won't be dealing with physical hardware, we'll be dealing with the hardware options through a little tool we're going to use. But there's something called adders and half adders. So if we already have a little kind of power tool for doing addition, wouldn't it be nice if we could just always do addition? So what we can do is we can get the 2's complement of one of our bottom number and then add it to the top number. And that gets us, so we do subtraction through addition. Make sense? All right. Binary coded decimals. So a few minutes ago we were talking about how convenient it is to go from decimal or from binary to hex and hex to binary. We have an issue. Decimal, our favorite numbering system, doesn't have that convenience. The compatibility between binary and hex happened to be in that concept of a 4-bit nibble. And 4 bits being the exact number of bits needed to represent a hexadecimal number. Right? 0 through 15, 16 unique values. Well, how do we get 10 unique values? Because that's our decimal numbering system, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. You have 10 unique digits in the decimal number system. How many bits does it take to exactly represent 10? Biggest digit is 9. How many bits does it take to represent a 9? Here's your options. 1, 2, 3, 4, 5, 6 bits. How many bits does it take to represent the number 9? Another quiz. How do you rate the number 9, the decimal number 9 in binary? One zero zero one. How many bits is that? 4. 1 0 0 1. 4 bits. How many bits does it take to represent the number 0? What's the number 0 in binary? 0. 1 bit. Can we represent 0 in 4 bits? 0 0 0 0? Sure. So is 4 bits the perfect size for representing decimal? It's capable of representing decimal. But are there some illegal binary values? Are there illegal 4-bit binary values that are outside of 0 through 9? For instance, what's the value 10 in binary? 1010? Is that a legal decimal number? Is it a legal decimal digit? Maybe that's the better way of asking it. 10 is not a legal decimal digit. It's a legal hexadecimal digit. It's A, but it's not a legal decimal digit. So 4 bits is compatible. We can represent 0 through 9 using 4 bits. But 4 bits is going to have some illegal values for decimal. Whereas 4 bits is exactly the correct fit for representing hex. So now, why binary coded decimal? Sometimes we hold decimal numbers that we don't intend to do math with. So here's this first question. When have you ever added 5 to your phone number? Oh yeah, my phone number is the same as Steve's, just add 5 to it. Doesn't make any sense, right? Yet, phone numbers are still made up of decimal digits, correct? But we don't need them to be mathable. I wonder if that's really a word.
Spell
Due to
check
the
says no.
fact that it's underlined on your.
Spell check
I'm gonna
says
guess
No, that's I wrote it that way.
no.
That it's underlined. That doesn't mean that it's not a word. It just means that I wasn't sure if it was a word when I wrote it. Ask Siri. Tell me about mathable. Siri will probably think I said something vulgar.
Mathable, copyrighted.
Okay.
It's
It's a game.
Is it?
it's
Ha!
as much as a word as Facebook is.
So you know what I'm talking about when I say mathable.
It
I
looks
can use it in a sentence. Able to be
Hasbro
mathed.
It looks like
Able
math
to be mathed.
Okay, math.
What's this?
It looks like math Scrabble.
Math Scrabble. That's called mathable. They have to pay me royalties for that, seeing as though I've
That's what the board looks like.
killing me. Okay. Similarly, have you ever added 215 to your social security number?
Only one fuck with the IRS.
So the reality is that those numbers aren't math-based numbers. They're data representation numbers, right? And why aren't we storing our social security number or our phone number in binary? You have a big long phone number. Okay. Why aren't we storing it? Why aren't we storing it in hexadecimal? Why not store our phone number in hexadecimal rather than binary? Rather than decimal. Wouldn't there be less digits to remember? Instead of area code, 262 353, blah blah blah. Why not just store it in decimal? I'm sorry, in hexadecimal.
We're using decimal.
Huh? We're used to decimal?
Everyone uses it.
Okay, that's fine, but I mean, everybody uses a lot of things. We still come up with upgrades, don't we? We come up with new ways and we get used to them.
Americans still use the imperial system. Why would we even think about switching out of decimal? We
Yeah.
still use inches and feet.
Give me a reason besides because we don't wanna. What's a legitimate reason for not using hexadecimal to represent our phone numbers rather than?
There's more digits or like values for digits.
Yeah, we have 16 different buttons that we have to maybe push in. Even though our phone number might only be 5 digits long, to produce that, we need to be able to press 16 buttons to work for all phone numbers, right? Well, now we have this weird balance. We like decimal because we're used to it. True statement. We are used to that. But it also has this nice balance of that's the number of keys we need for a telephone, for example. Right? Or if we look at the top line of your keyboard, we have all our numbers, all our decimal numbers in there, and we don't have enough digits there for hex. We have to make bigger keyboards. So I have 4 extra digits. One of them is the tilde. Then I have a slash, not a slash. I have a hyphen or a minus sign, equal sign, or a plus sign, and then the delete button. Outside of that, so I don't have 15. I don't have 15 keys.
I don't know if your definition of it doesn't need to be mathable is too true because IPv6, it's not mathable, but it's also using hex.
Well, the mathable part has nothing to do with decimal. It has to do with this idea of binary coded decimal.
Oh, okay.
Yeah, it's this concept that often we have numbers that we don't need to have. We don't have to do mathematical operations on them.
Yeah.
Therefore, it would be acceptable if we can find a convenient alternate representation for them. Correct? Be acceptable. As long as we don't do math with them. It would be acceptable. Okay? So we can store them in a more convenient representation that isn't compatible to math operations. And here's an example. So converting binary coded decimal, BCD, to decimal. Decimal digit 0 is 0000. Decimal digit 1, 0001. Decimal digit 2, 0010. 3, so on and so forth, all the way up to 9, just as expected. But then we have this group of 4-bit, so this group of nibbles, which represent invalid decimal terms, decimal fields. That makes sense? Okay, so for homework, write a converter. Here, I'll put it in here. Or Excel if you choose, although I think everybody who has 250 right now has enough stuff to do this assignment. So we're going to write a converter in Java where we're going to have a method for BCD to decimal and a method for decimal to BCD. So the decimal one will take in an int val and it will return the string version of that in BCD. The BCD to decimal will take in a string s and it will return the decimal integer. Make sense? Okay, so little Java practice for you writing that conversion tool. Okay, questions, comments, concerns, bribes. I'll see everybody on Tuesday.